Good afternoon, everyone. Welcome to the next installment of the Quantum AI Speaker Lecture Series. Today, we're going to be hearing from Professor Garnet Chan, who is now a professor at Caltech, having very recently moved from Princeton, where he was a professor for several years before he was at Cornell. Garnet's group is known for being one of the most sort of prominent research groups in the development of methods for electronic structure theory, which comprises theoretical chemistry and also some material science. So in particular, his group is known for developing very efficient, high accuracy methods for simulating quantum systems, and also techniques for sort of using those high precision methods to gain useful insights about real systems. So without further ado, here's Professor Chan.
All right, thanks, Ryan. Let's just make sure it's all working. Okay, great. So because I can only sort of think of one side at a time, I'll mainly point at this side if I'm going to point. Okay, so it's really great to be here, and this is the first time I've ever been on a Google campus, so it's very interesting to see how it's all laid out. And I've already had a chance to sample some of the free food, and it was great. And I can remember periods in my life where I basically go anywhere if free food was offered. So that's one of the reasons why I'm here. But of course, now's the time to do some work, and so here I'm going to tell you a little bit about some of my research. So the title of my talk is Simulating the Quantum World on a Classical Computer. But before I sort of get into the talk, I'll just say a little bit about the level that this talk is pitched at. So when I was putting this talk together, I emailed Ryan, my host, and asked, what sort of people are going to attend? And he said, well, they're going to be people who are experts in quantum mechanics and quantum computation. There'll be some of the people. And then there are going to be people who are sort of general computer scientists who are very tech savvy but might not really be physicists. And then in addition, there might be people, this might be on YouTube, and there might be people anywhere in the world watching it. So I'm used to teaching classes in college where you have a range of abilities, a range of backgrounds, but that's a really big spread in preparation for this talk. And so what I've tried to do, and this will be an experiment, is I've tried to make a talk which has a little bit of something for each of those three kinds of audience members. And so if you're someone who is an expert in quantum mechanics, studies quantum computing, then just sit back and relax and have a little fun with me in the first half of this talk, and we'll get to the sort of the detailed technical stuff towards the end. And if you're someone who really doesn't know any quantum mechanics, then I'm really going to try and hold your hand all through the first half of this talk and try and teach you some quantum mechanics. And then when I get to the second half, I'll let go of your hand, but hopefully you'll have absorbed enough that the general gist of what I'm trying to say will make some sense. Okay, so let's start, and let's start with who I am and perhaps what I am. So I'm a theoretical chemist, and that means I'm the kind of chemist who doesn't do any experiments. And in fact, I remember precisely the last time I did an experiment, and it wasn't actually so long ago. It was 6 years ago in 2010, and it was when I was doing some community outreach in an elementary school, and teaching the little children how to make batteries out of a piece of fruit and some pencil lead. And I distinctly remember, out of the various things on that day, not being able to do that experiment. So there's a picture of me where the kids are kind of helping me with my battery, and that's why I've ended up a theorist. So what do I do as a theoretical chemist? Well, in essence, what I try and do is I try and simulate the world of chemistry on a computer rather than do experiments. And since the world of chemistry is a world of atoms and molecules, and the atoms and molecules are governed by the laws of quantum mechanics, this is basically the same thing as simulating the quantum world. So in the first part of the talk, I'm going to try and explain what quantum mechanics is and what the quantum world is, and then look at why trying to carry out the simulation of this world appears to be very hard if you just have the kinds of computers that we have today, so classical computers. And then in the second half of this talk, I will sort of turn this question on its head and point out some of the reasons why we now believe actually simulating quantum mechanics isn't as hard as we first thought, and can in fact be done on classical computers. And I'll give you some reasons why this is the case and some examples of these simulations. And the reason why this complexity of quantum mechanics is often really just an illusion is actually related to many ideas that would be familiar if you have a background in computer science from machine learning. And so I'll draw the connections to machine learning and, of course, the implications for quantum computing at the end of the talk. OK, but first let's begin with what the quantum world is. And so the quantum world is the world of atoms and molecules. And understanding that the world around us is made of these discrete units, atoms and molecules, is perhaps one of the most fundamental insights we've ever achieved as a human race. And that's something that Richard Feynman, of course, the famous physicist at Caltech, pointed out very eloquently, where he said, well, if all of humanity's knowledge was wiped out in some sort of catastrophic event, and you could only preserve one piece of wisdom to pass on to future generations, what would that be? And as he argued, that would be the fact that all things are made of atoms. Now, for such an important fact, you'd think we would have known about this for a very long time. But as it turns out, the acceptance of this atomic hypothesis is a relatively recent event. I mean, even up to 100 years ago, whether or not matter was discrete, in other words, made up of individual units, or just some continuous substance, was widely debated. 100 years is not such a long time. I mean, there are people on the planet who are more than 100 years old, so they were around when this was a question that people thought about. The debate was finally settled in a nice collaboration between some theoretical ideas from Einstein and careful experiments by a French physicist called Perrins, who was a Nobel laureate in the early part of the 20th century. And the experiment he carried out was to take some very fine particulate matter, so that could be like a pollen grain, or it could be, say, a starch granule. If you take a potato and squeeze it, you can get some starch granules out. And you place that grain on the surface of a fluid, so that might be like some water. And you observe what happens under the microscope. Now, if the fluid, water, is really a continuous substance, and you ask, well, what should I expect to see for the motion of the pollen grain? Well, perhaps the pollen grain will stay stationary, or if there are some currents, it should move smoothly around the surface of the water. But that's not what you see. What you actually observe, if you follow the path of the pollen grain, is you see this very jagged motion where the particle seems to change direction very abruptly at various points in time. And the only reasonable way of explaining what happens, and this was what Einstein worked out, was to deduce that water is not actually a continuous substance, but made up of little bits, atoms and molecules. And these abrupt changes of direction correspond to those molecules bumping randomly at random times into the pollen grain or starch granule, imparting some momentum. OK, so this was really the experiment that sort of convinced scientists that the world is made of discrete units, atoms and molecules. But as you see, it's really quite an indirect type of evidence. And if we go now to the 21st century, to the modern day, we have much clearer evidence that atoms exist. And perhaps the most evocative image of the reality of atoms is provided by an instrument known as the scanning tunneling microscope. The scanning tunneling microscope is in essence, just a circuit which has a battery and some wires sticking out. And the special thing about the wire is that the tip of the wire is extremely sharp. So you can make these wires so sharp at the bottom that they're essentially just one atom sharp or one atom thick at the very end. And the way you use this microscope is you attach it to a material. So you attach one end of the wire to the material, and you take the other end and bring it around and bring the tip all the way down to the surface of the material. Now, if you made the tip touch the material itself, then you'd complete the circuit and a current would flow. But as it turns out, you don't have to bring the tip all the way down to the surface. You can leave a little gap, and some current will still cross that little gap. That's called tunneling of the current. And the amount of current that crosses that gap, the strength of the current, depends on the distance from the surface of the material you're studying. And so because atoms are kind of round, So if you move the tip and it goes across the sort of top round bit of the atom, you get a lot of current because you're close to the top of the atom. And you move into the bits in between the atoms where you kind of the atoms dip down, you'll see a small current. And you can register this as you move the tip, scan it back and forth. And so you can see an image where you produce the image of the shape of the atoms with the scanning tunneling microscope. And this is a beautiful example of corporate research because the scanning tunneling microscope was developed at IBM, as you can see. It turns out that you can even pick up atoms with this technique. If you bring it down, the atoms like to stick to the tip. And so they position the atoms and scanned by moving the tip across to produce this very nice image. Now almost 30 years ago. So today, we do have direct evidence of atoms, and we can even manipulate the atoms themselves. We can pick them up with these very precise machines. But these are not easy experiments, and these are not cheap pieces of equipment. You don't have them in your kitchen. And fundamentally, even though we can directly access atoms, it's never going to be an easy task to directly interrogate them. And the answer is the reason for this is just very simple. It's because humans, we have these like fat, pudgy fingers, right? And atoms are extremely small. And they're 10 orders of magnitude in scale between the size of the human finger and the size of an atom. And trying to bridge this scale experimentally is always going to be a challenge. And so that motivates a different way to try to interrogate the world of atoms and molecules. And that's to not try to study it experimentally, but to try and recreate it digitally inside a computer. And so you can study just the simulation of the atoms inside your silicon chip rather than having to carry out a complicated experiment. So the goal of this type of project is to really produce the same sort of thing as you see in the movie The Matrix, right? So if you remember in The Matrix, what you had was some race of beings who had created some simulation of the world which was so realistic that when you stuck the humans inside of them, they couldn't tell if that world was real or if it was a simulation. And that's what we're really trying to achieve now, but for the more modest goal of simulating the worlds of atoms and molecules, not the entire world around us. Now, of course, when I say simulate this world, I don't mean generate computer graphics or some kind of animation. You really want it to be actually faithful to the true world. And that means that we have to follow the physical laws that govern atoms and molecules, which are the laws of quantum mechanics, and trying to faithfully emulate these laws as precisely as possible on a computer is a goal of what I try to do and essentially what my whole field of research, quantum chemistry, is about. Now, if you're not a scientist, and perhaps not everyone in this room is a scientist, this statement is sometimes surprising, and this statement is perhaps less surprising if you are a scientist. It turns out that the laws of nature are, in fact, for all intents and purposes, completely known. Aside from some very, very extreme cases, for example, at the very, very beginning of the universe, just after the Big Bang, or perhaps on some minute scales of 10 to minus 35 meters, something basically you will never probe experimentally, we know exactly how all the fundamental particles work and how they interact with each other. And if you make this kind of statement, you can have sort of two kinds of reactions. So you might have the reaction, well, we know all the fundamental laws of physics. Well, that's the end of physics. That's the end of the world. And one can adopt that attitude. But actually, what most people think today, and the attitude that I have myself, is that actually this is not the end of the road, but it's the beginning of a new and beautiful journey. And the reason why it's the start of a new journey is because just because we know the behavior of the individual particles and how they interact with each other in pairs, this doesn't mean we understand how all those interactions combine when you have assemblies of thousands or millions or billions of particles to produce all the complexity that we see in the world around us, like life, for example. So the situation, I would say, in physics today can be illustrated by a chess analogy. So the way physics is today, we basically know the rules of chess. We know all the rules of chess. There aren't any missing rules like capturing a pawn en passant that we haven't yet put into the game. So we know all the rules of chess. But even though we know the rules of chess, that's a very different thing from understanding how those rules build on top of each other when there are many pieces in a game, and you apply the rules many times to generate the game of chess. So this fact that having just lots of stuff around, even if you know the fundamental laws, can generate some unexpected complexity, which is really encapsulated in a nice phrase by my former colleague at Princeton, Phil Anderson, that more is different. And more is especially different when you go into the world of quantum mechanics. So when you have many quantum particles interacting, they can produce some truly exotic and unexpected behavior. And it's a challenge of capturing these unexpected types of phenomena that is the challenge of simulating the quantum world. OK, so now let me talk a little bit about quantum mechanics and what the quantum world is. And to sort of place quantum mechanics in perspective, it's useful to understand where we apply it as physicists, the kinds of phenomenon we apply it to as physicists. And so we can divide the phenomena in the universe or in the world into sort of different categories based on length and time scales. And so on the larger scales of the universe, then really the right theory to use to answer questions people pose, like why are galaxies distributed the way they are in space, is a theory of general relativity. And then when we go down perhaps to the human scale, which is a scale of about a meter in size or a second in time, then the sort of most convenient theory to apply is the good old Newtonian mechanics that Isaac Newton worked out 400 years ago. I mean, it's not an exact theory. It's an approximate theory, but it works so well that, and it's so easy to do, that that's the best thing to do for human-sized phenomena. And then when you go beneath that scale, down to, say, 10 to the minus 6 meters or below, then that's the regime where quantum mechanical effects become important. So I like to say that quantum mechanics is really the theory of the small, but even though it's the theory of the small, it has very big consequences, because almost all the properties of materials that you see around you cannot arise if you just do classical mechanics. They arise due to intrinsic quantum mechanical behavior. So if I were to look at, say, ask like why is a material a certain color, or why is something a metal and why is something an insulator, or even something like if I take a gecko, why is the feet sticky? These are all things that arise due to quantum effects, and they don't exist in the classical theory or in relativity. OK, so we're going to look at quantum mechanics applied to atoms and molecules. And if the last time you did physics or chemistry was in high school, then this would maybe your picture of an atom. So you have a nucleus, and the electrons are fizzing around in orbits. And maybe if you did AP chemistry, then you'd also learn that the molecule has bonds in it, and those bonds are made by sharing pairs of electrons with each other. Now, since everyone in the room is an adult, so I think it's safe that I can say this, that everything you learn in high school chemistry or physics is a complete lie, right? It's all completely false. Because that's not really what an atom looks like. It doesn't look like this. You don't have these well-defined particles going in nice orbits. Really, an atom is kind of fuzzy. And that's a general feature in quantum mechanics, that everything that you think of as normally being a very well-defined object is kind of fuzzy around the edges. Now, fuzzy is not a very precise term, but the technical term for fuzziness is that things behave like waves. And so the motion of a fuzzy particle is not the motion of a point-like particle. It's a motion of a wave. And we see this from the following. So if you imagine a non-fuzzy particle, like a billiard ball, okay, it's very sort of discrete and hard, and you think of how it moves through space, you can describe its position, for example, from its center of mass at every point in time. That's very, very clear. But if I take a fuzzy object, its fuzziness means that it has some shape. And if it has some shape, then while traveling, the shape can also distort. So a fuzzy object will be something whose shape can change with time. And mathematically, the motion of something with shapes is just wave motion. A wave is just something that has a waveform, and that waveform, it can move around, and the waveform, the shape, can change with time. So the individual quantum particles like the electron or like the proton and so on and so forth, they have this intrinsic fuzziness, which means that when they move around, the motion is best described by mathematical equations, which look like the equations that describe waves. Now, the juxtaposition of these two words, wave and particle, that in colloquial usage have very different meanings, causes all sorts of angst when you first come across quantum mechanics. And you can see this angst when you go into the internet. And let's say you type something into a search engine, like Yahoo. And I report here something that I actually, the precise verbatim thing that came up when I searched for wave-particle duality. So it's this thing on Yahoo Answers. Right? In quantum physics, how come one particle could exist in multiple places? Duh. It's notable because I don't know if that's a question or an answer, actually. But the basic issue is, of course, if something is fuzzy around the edges, it's quite hard to say where it is. So if you were to look at a wave, just a classical water wave, and you to say, well, is it here, or is it here, or is it there? Or maybe it's a little bit in all the places. Well, it's not entirely clear what you would answer. And there's the same difficulty in answering the question about where fuzzy particle is in quantum mechanics. So if I take this fuzzy electron and I say, is it here, is it here, is it here? I carry some measurements to detect where it is. You will actually find that your measurements report that some percent of the time, they'll read out that the electron is here, and some percent of the time, they'll read out the electrons here, and some percent of the time, they'll read out the electrons there. Okay, so quantum mechanics, because of its fuzziness, gives rise to an intrinsic probabilistic spread in the results of measurements. If you ask, is something going this way or that way, you don't get a definite answer. You get just some probability that you see this or that. So another way that we can think about this fuzziness is that really the particle is a combination of different scenarios for different measurements. So a single particle, if you carry a measurement, might seem to be here 10% of the time, and here 20% of the time, and here 40% of the time. And so I can actually think of a particle as being a superposition of all these possibilities weighted by some probabilities. And I can write down a function, a probability function, probability density, for observing, say, the particle here or here or here. And this probability density is just one step removed from the most fundamental object in quantum mechanics, which is the wave function, which is the quantity on the right-hand side. And so this wave function is the mathematical object that behaves a bit like a wave, but it really is a wave of probabilities of different measurements. That's the wave that is being propagated in the equations. And indeed, if I look at the mathematical equation for a water wave, it basically tells you the height of the wave at different positions on this coordinate. And this mathematical equation looks almost exactly like the quantum wave equation, except the only difference is now we interpret this height of the wave that's being solved for mathematically as telling you the probability of seeing different things in your quantum mechanical experiments. Now, you can ask, well, how do I solve this equation? It's a differential equation. And in certain simple cases, you can solve it on a piece of paper. And like when we teach this to our undergraduates, you give them the special, very special problems where they can solve it on a piece of paper. But let's say you can't solve it on a piece of paper. It turns out this equation is still very easy to solve on a computer. Because if I take this sort of probability wave, you want to find out its value at different positions in space. So what you do on your computer is you put down a grid in space, maybe 1 billion points. But 1 billion points, 1 billion numbers, is a very small set of numbers for a modern computer. Okay, so even if you put down this very, very dense grid with with many, many points all over space to try and solve this equation, it's actually very easy to do. So solving this kind of Schrodinger equation is essentially trivial on modern fast computers. And so does this mean that simulating quantum mechanics is very easy? They told you the equations are easy to solve. And the answer is, well, no, because so far I've only talked about a single particle. So now let me talk about two-particle and many-particle quantum mechanics, which is where things start to become mysterious and harder. OK, so first, let's talk about two particles. I'm going to illustrate in some abstract way, because I don't know how to draw it out, some quantum state of two particles, let's say somewhere distributed in the box. And in just the same way that I could think about the state of one particle, one fuzzy electron, as being a mixture of probabilities of an electron being here, or an electron being here, and an electron being there, I can similarly think of the state of two particles as being some superposition or mixture, perhaps of the two electrons being distributed like this, or the two electrons being distributed like this. That'd be just an example of a fuzzy state of the two particles. Now the interesting thing about this particular mixture of positions is that it actually has what we call a correlation between the particle positions. In other words, if I just look at these two as a set of possibilities for what the system's doing, you'll notice that if I make a measurement and I see a particle on the left-hand side of the box, then you will know, because the system's only made of these two possibilities, that there will be a particle always on the right-hand side of the box. So the two particles always seem to be correlated. If you measure one on the left, then the other one will be found on the right. If you measure one on the right, one will be found on the left. So there's correlations between the properties, between the measurements on individual particles, is what is known as quantum entanglement. Now, entanglement is yes another of those aspects of quantum mechanics which causes a lot of confusion and makes people unhappy. And so once again, if you go to Yahoo Answers, you see something like this. I read about this phenomenon, seam quantum entanglement, transmit data with infinite speed. Is this correct? Now, you know it's the internet, so of course it's not correct. And this is the most common misconception about entanglement, that it allows particles to transmit data very quickly between places. But I think it's worth understanding how this misconception arises. And this misconception arises because we build a mental model that is actually has a flaw in it. Okay, so the way in which you can look at a problem that makes it seem as if data is being transmitted with infinite speed is the following. So if I say, let's take the same system that exists in the superposition of these two possibilities, and I ask, what's the probability just overall of seeing a blue particle on the left or the right? You'll find that there's a 50% chance of the blue particle on the left, and a 50% chance that the blue particle on the right. And the way we usually think about this is that this is an intrinsic property of the particle. In other words, if you are the blue particle, then you'll have a 50% chance of being a left blue particle, a 50% chance of being a right blue particle. And similarly, you can say the same thing for the red particle, right? So you can say, well, if I'm the red particle and you look at it, then there's a 50% chance that it's on the left or the right. And you think of that as an intrinsic property of the red particle. And so it becomes very mysterious with this kind of mindset that if you find the blue particle on the left, then all of a sudden, you see the red particle with 100% probability on the right. You seem to have changed some fundamental intrinsic property of the red particle. And if you think from that kind of mindset, then it seems like the blue particle has told the red particle to suddenly appear on the right. And this is what makes people think that you can transmit information through entanglement. But it's, of course, just the wrong mental picture, because what your mind is really constructing is sort of the following. So when I tell you there's a 50% chance to see red particles on the left or right, you make this mental image of where the particles are. And then when you say there's a 50% chance of blue particle on the left or right, you make this mental image. And then for the total combined states of the two particles, inside your head, it's most natural to think that it really looks like this, that there's a 25% probability that the system is in this state, or in this state, or in this state, or in this state. But in actuality, there's no reason why, when I built the quantum state of two particles, that I had to prepare it in such a way that it has this set of probabilities associated with it. In fact, the particular quantum state I prepared did not even have these two possibilities. It was just a mixture of these two. And so all that's happening when you see the kind of odd effects of entanglement is it just reflects the way that the quantum state was prepared in the beginning, not as perhaps the most intuitive superposition of states where all these possibilities are allowed, but as perhaps some slightly non-intuitive or peculiar combination. Okay. Now, so far I've been talking about one particle, two particles. You'll notice that even when I was talking about two particles, even if these particles only had the property that they could be on the left or the right, there are still four possibilities that I had to keep track of in principle for the different possible things I could see, right? So I have to keep track of the probability that I see this event, or the probability that they distribute like this, or like this, or like this. So there are four possibilities there. And I've written down numbers. 0 means particles on the left, 1 is particle on the right, and the probabilities are this function psi. Now, it's not hard to see that if I now go from two particles to many, many more particles, let's say 1,000 particles, that you'd have to keep track of many, many more probabilities. So in particular, if I had 1,000 particles, and each particle could be either on the left or the right, and I had to keep track of all these possible configurations that can be mixed together in the quantum state, then I'd have to write this wave function that is a function of a binary string of numbers where you have 1,000 zeros or ones, and that's an enormous set of numbers. So that's 2 to the 1,000. This is not correct. That's 10 to the 300. But in any case, it's a very, very large number of possibilities. And it's this gigantic blossoming of possible ways of particles behaving simultaneously that makes more in quantum mechanics very, very hard. This leads to a kind of depressing viewpoint on quantum mechanics, because what we're saying is we know these fundamental equations of nature, but when you have more than just a handful of particles, you have to keep track of an exponential set of possibilities, and that just doesn't seem feasible. And indeed, if you were go back to the 20th century, you see statements written all the time that are really quite depressing. So, for example, this is from the year 2000. David Pines and Bob Laughlin, both very famous people. Bob Laughlin was a Nobel laureate in physics for the fractional quantum Hall effect. And he wrote the Schrodinger equation cannot be solved accurately when the number of particles exceeds about 10. And then they go on to make the precise prediction that no computer existing, or that will ever exist, can break this barrier because of the catastrophe of dimension, by which they simply mean that if you increase the number of particles and have to count how many possibilities for the joint behaviors of all these particles, it's growing so rapidly that you will never be able to tackle it on an ordinary computer. But what we've really learned, though, in the last 15 years, the time since this type of statement used to be popular, is that this complexity is, in almost all cases, not actually really there. It's what we call an illusion of complexity. It appears to be there when you write the equations down at first, but if you actually look in the world around you for it, you don't actually see it. So basically, there are all these possibilities for how a quantum system will behave, but they're just very, very hard to observe. So a concrete example of this is if you take Schrodinger's cat. Okay? So Schrodinger's cat is a quantum state that's a mixture of the state where all the atoms are in such a way that the cat is dead, with a cat whose atoms are in such a state that the cat's alive. Okay? And so you can take, it's a valid quantum state to say I'm in this fuzzy picture where the cat is 50% dead and 50% alive. But as we all know, if you actually try to look for Schrodinger's cat, you never see Schrodinger's cat in reality. So for most physical systems, I like this cartoon. Yeah. So for most physical systems, this exponential set of possibilities is not real. And you can sort of go back and ask why does nature not allow this complete exponential set of possibilities, at least at the energy scales that we usually look at? And the deep reason is that we live in quite a special type of world. It's not like a world where you have arbitrary interactions between all the particles. So if you take the fundamental particles, they only interact pairwise at a time. And the interactions between the pairs of particles are very simple. So if I were to take in atoms and molecules, the Coulomb's law, Coulomb interaction, is just something that's strong a strong interaction when the particles are close together, and when you go very far away, it sort of dies off to zero. So it's this very simple nature of these interactions, which are essentially applied many, many times. So when you have a system that is where the electrons are bumping off each other many, many times, they fill these interactions many, many times. These simple interactions impart the structure to the resulting quantum states that we see and make them also correspondingly very simple. So the type of possibilities that we see, the type of superpositions of many particle states that are physically relevant are not these generally entangled states, which are mixtures of arbitrary possibilities for the quantum systems, but only what are so-called locally entangled states. And by local entanglement, I kind of mean that that if you take a system with particles that are sort of stuck in a small region of space, then over this small region of space, you do need to keep track of all the possibilities for what the quantum particles can do simultaneously. But if I go to a larger problem, where you have sort of well-separated regions for the different quantum particles, then if you find that if you make measurements on, say, the part of the system here and the part of the system which is outside the door, then in the typical state that we see in the world, there's no correlation between those measurements. They behave as if they're independent. And so this locality principle, or this principle that you generally only see local entanglement, means that you don't need to keep track of this exponentially growing set of possibilities, but only the possibilities that occur together in small nearby regions of space. And so this removes the complexity, and one can see in some qualitative sense. And then the technical question is, how do I rewrite the laws of quantum mechanics or rewrite the mathematics of quantum mechanics to build this physical simplification in? OK, so to do this, I'm going to have to introduce what entanglement is in a slightly more mathematical way, but not much more. So consider a system which has got two regions in it. Okay, so it's got a left region, it's got a right region, okay, 1 and 2. And this symbol n will denote some property that you measure in the region. So for example, you might think n denotes the number of particles you find in a given region. So you can write down your wave function, which describes the probabilities of finding a set of particles in region 1 and a set of particles in region 2. And if you have no entanglement, then this wave function, this probability function, would just factorize. So that tells you, because the probability is factorized, that there's no correlations between measurements in regions 1 and 2. OK, so what does it mean if you have an entangled state? Well, in that case, this wave function doesn't factorize. And instead of writing it just as a product of probabilities, you now have to write it as a sum over products of probabilities. And there's this index of summation here. And it's this summation over many types of products of probabilities which generates the entanglement. Loosely speaking, if you have more terms in the sum, then you have more entanglement in the system. And you can think of these individual probabilities appearing now as kind of conditional probability amplitudes. So this basically says, what's the probability of measuring the property n1 in region 1 given some information I that has been communicated from the neighboring state 2? OK, neighboring region 2. OK, so we can see now mathematically how you can generate entanglement just in these mathematical symbols. And that now allows me to explain what I mean by local entanglement. So in a state with local entanglement, let's first consider a system, well, with 3 spatial regions. So let's generalize it a little bit. And first, the state with no entanglement, this probability, this wave function, probability amplitude, then again just factorizes into 3 sets of probabilities. And now I know that if I want to put entanglement back into the system, I have to write it as a set of sums of probabilities. But I write in a special way so that only locally regions are coupled together. And so this would be a locally entangled state, where I'm now summing over sets of probabilities associated with regions 1, 2, and 3. But the summation is such that the probabilities in regions 1 and 2 are directly coupled, and the conditional probabilities in 2 and 3 are directly coupled. So if it were a more general entangled state, I would also have to couple 1 and 3 as a region. And so this is a mathematical form of the wave function where there's only entanglement explicitly between regions 1 and 2 and 2 and 3, which if you imagine the regions on the line, means that the entanglement is only present locally. So I can generalize that to arbitrary regions. So let me now not just have 3 regions, but an arbitrary number of regions, L regions. And now this complicated wave function is again written as a product of probabilities that are all coupled together in this local way. And usually, this is a formula with lots and lots of variables and indices. And it's kind of tricky to write out all the time like this. So usually we use a notation that is more of a picture. And so I say, well, on this left-hand side, I have this gigantic set of numbers. It's a gigantic array of numbers that's inside the wave function, or gigantic tensor. And I draw this array or tensor like this, where these are the indices of the array or the tensor. Here I've just drawn 3 indices, not L indices, but just for simplicity. And then this type of approximation to this tensor is equivalent by saying I can rewrite this picture in terms of these little probability objects, these lower dimensional tensors, lower ranked tensors, and connect them all together, sum them over these indices I1, I2, which is denoted by these bonds. Now, the achievement in reduction complexity, moving from this picture for storage, is of course immense, because on the left-hand side, you have an exponential set of numbers, an exponential large set of numbers in the tensor. And on the right-hand side, you only have a linear complexity in terms of how much storage you have as the system size grows. So going from an exponential to a linear is, of course, this is, of course, an amazing reduction in cost. But the only reason why we can achieve this is because the types of states we see around us are very, very special quantum states, not the arbitrary types of quantum states in principle allowed. OK. So here I've generated local entanglement in some very one-dimensional-like way. I've joined region 1 to 2, 2 to 3, 3 to 4, and so on and so forth. But you can, of course, connect these regions in an arbitrary network. And so, for example, this was the connection I showed earlier that's suitable in a one-dimensional geometry. And this is something known as a matrix product state, which people have studied in physics for more than 20 years now. But you can also consider other ways of joining all these tensors together. And this would be an example of how you join them together to describe a 2-dimensional system. And you could join them in a cube to describe a 3-dimensional system, and so on and so forth. OK. So all this now presents a concrete mathematical machinery to write down only the relevant quantum states that actually occur in nature. And we can now use this machinery to actually carry out a simulation, not just for 1 particle, 2 particles, or 10 particles, but really for hundreds of particles. And this is something that my group has done over the last few years. And you can see, I was just for a few examples of this. So this would be a simulation on the active site of the oxygen evolving complex, which is all the heart of photosynthesis. So if you think, what is it that plants do? Right? They take sunlight in, and they convert water into oxygen and other things. And it all takes place in a few atoms in the middle of an enzyme. And I'm going to show those few atoms here. I mean, they're surrounded by all sorts of gunk, but I just show the important atoms. And if I were to try and write down a wave function that described all the possible quantum behaviors of the electrons in these atoms, even making lots and lots of simplifications, it would require a very large number of elements, about 10 to the 18 elements. But if I instead build a wave function by writing down tensors on each of the atoms, in fact, you write down a few tensors on each atom because there's more than 1 electron per atom, then you can represent this wave function essentially all the way down to numerical precision, in other words, essentially numerically exactly, with a very, very small number of elements. And given this parameterization, I can solve the wave equation, the Schrodinger equation, and I can ask questions about how this molecule behaves. And this, for example, is just a pretty picture that just shows you how the entanglement is spread out across this molecule. I'll show you another example, which I think realizes the dream we had in the beginning of realizing the matrix, for atoms and molecules. In other words, recreating the world of atoms and molecules so precisely that we can't tell the difference between the simulation and the experiment. And so this is something that we did for simple material, which is benzene crystal, just crystallized organic system. And here we asked a simple question about this material, which is what's the amount of energy that's holding the material together? That's the so-called lattice energy. And you can do this calculation, and it has lots of terms in it. And so you compute all these different terms, and you add them all up. And then you obtain a number which is the theoretical estimate just from quantum mechanics and with no other assumptions for the lattice energy of the system. Now this is a model material that has been studied many, many times. And this lattice energy has been measured through many, many experiments. And there's an accepted experimental number. And the accepted experimental number is this number here, 51.5 kilojoules versus 56 kilojoules. Now you might say, that's not so different. That's pretty good, right? But actually, they don't actually agree within the error bars. And so that leads you to two inescapable conclusions, only one of which could be right. Okay? And assuming that we haven't actually made a mistake in what we were doing, so either because all we did was solve quantum mechanics as exactly as possible, if we see this disagreement, either you led to the conclusion that quantum mechanics is wrong, or you led to the conclusion that all the experiments are wrong. And of course, the answer is that the experiments are wrong, right? So if you go back and look at what the experimenters are measuring, they see something on the dial, and they write it down in the lab book, and then they have to interpret what that number is. And there's a lot of stuff that's hidden in the interpretation of the experimental number. And if you go back through the experimental literature and do that interpretation more carefully and more accurately, that will bring that experimental number back up into agreement with theory, which is really how a theorist likes the world to work, and is an example of a case where we really can simulate the world of atoms and molecules in a real material more precisely now than we can measure it with accurate experiment. OK, now let me, I don't know what the time is, but I think I'm coming towards the end. Is that right? So let me finish with a few slides that explain why I'm down here today. So the Google and I. This has got two parts. And the first part is the following. If I take tensor networks and I describe them, which was this way I wrote down the wave function, right? And I describe them just in an abstract mathematical way, then they represent the nonlinear parameterization of a complicated many-variable function. And there might be some of you who have seen this type of phrase used in a different setting, because an artificial neural network is also just a nonlinear parameterization of a complicated many-variable function. And so you can ask, well, is this similarity a deep analogy, or is it just words? And the answer to this isn't, no one really knows for sure right now, but it really looks like there's a very compelling resemblance between the two. Because if I look, for example, at a tensor network we didn't discuss, this is a mirror, but we didn't talk about this one, but this is one that people also use. This picture looks really very similar to this picture. Now, the individual symbols in the picture actually do not mean the same thing. So, for example, each of these lines here represents a summation. Now, in this type of neural network picture, this just means an input. Okay, so the lines are not, so that it's not a direct equivalence, but there's clearly a lot of analogies between the two. And so one can then ask the question, well, let's say it is a deep analogy. Then what are the implications? So one of the first implications would be to say, well, we know a lot about physics, quantum physics, and the physics of tensor networks, and we have all these well-defined theories, renormalization group, theory of entanglement, that we use to understand tensor networks. Well, perhaps these can be used to understand how neural networks actually work, or say, for example, how deep learning works. And people actually have begun to embark on this task. And there's, for example, a paper which I think is well known by now from Mehta and Schwab, which maps the renormalization group, which lies behind tensor network algorithms, onto the structure of deep learning and vice versa. Now, another implication is we have so many artificial neural networks in the world. I'm very new to this field, and all I can say is, every time I read it, you can say, what's an artificial neural network? Well, there's like millions of different kinds, right? Millions of examples. And so perhaps some of these neural networks may, in fact, be useful in quantum simulations. And there are quite a few people who are actually thinking about this, but the first paper that appeared is from Matthias Troyer's group, where they actually use a type of neural network, I think called a recursive Boltz machine to simulate some quantum many-body physics. And then the final thing is, a final connection is, even if we stay within these tensor approximations, these networks of our respective domains. So let's say I just want to work with tensor networks in physics and chemistry, because that's what I feel comfortable with. Nonetheless, there are all sorts of algorithms and optimization algorithms, for example, gradient descent algorithms and backpropagation, all these kinds of things, which were invented in the artificial neural network community, which actually haven't been applied in the regime of physics simulations. And you can try and transport this information from one community to the other. And so that's something that we did very recently, for example, just as a little fun project, where we implemented a calculation using a tensor network representation of the wave function. But we did it inside TensorFlow. So we repurposed the neural network type architecture TensorFlow to do these quantum simulations. And this allowed us to do, for example, automatic differentiation, which had never been used in tensor network simulations before. And here's just showing a simulation of the hydrogen cluster using the typical gradient descent algorithm in TensorFlow. So I'd like to, it's really the beginning of this field that's at the interface between machine learning and many-body quantum physics. And it's something that I and others in the field are very interested in. And it's something that I think would be interesting to have a conversation with people here at Google who have so much expertise in the machine learning side, especially. OK. Now, the second reason why I'm here, the second part of the Google and I, is probably what I'm going to spend most of my time today doing. And you'll notice that everything that I've been talking about has been trying to simulate quantum mechanics, but using the computers we already have, or the Intel chips. And you have a quantum AI group here, and they're trying to build a quantum computer. And one of the things they're trying to use the quantum computer for is to do quantum simulations. And so the key question to answer there, if you want to establish so-called quantum supremacy, where you can show a quantum computer is better than a classical computer in every possible aspect, is to try to find the type of quantum problem which you cannot simulate on a classical computer and then get them to do it, right? Get the quantum AI lab to do it. And so trying to understand the crossover between the classical and quantum simulations of the quantum world is really a very important question to answer if quantum computing is to become an accepted and useful tool for physical simulations. OK, and so that's pretty much it. So that brings me pretty much to the end. So I gave you, as I mentioned at the beginning, a kind of slightly odd talk today that was kind of pitched at different levels. And I only sort of talked a little bit about one part of my research. But generally speaking, in my group, we try and understand many particle quantum mechanics with tools from chemistry, physics, and computer science. We work a lot on methods, like the tensor network methods I showed you before. We think about different kinds of material applications. And that's basically it. So if you're at Caltech, come and visit. And thank you all for your attention.
If anyone has any questions, you can go ahead and ask.
So when you were talking about the how many interactions that you needed to simulate in the early part of the talk, and I guess that was still while you were in the simple part. So you were basically talking about things in a kind of a 1D manner where you only had two particles interacting at a time.
Yeah, and they could only be left or right,
But then you got to benzene. And the first thing I was thinking of was, OK, well, what about aromatics, where you've got sort of fundamental interactions between 6 electrons at a time? And I thought about benzene, and I thought, well, but benzene has all these symmetries, so what about toluene? Just break the symmetry that way.
Yeah.
How hard is it to completely simulate toluene? I mean, I suppose it's easier than the photosynthesis thing.
Yeah, so you don't really need to make any assumptions of symmetry in the calculations. And so the idea that you want to, so the general framework, in principle and in practice, not all of this is developed, but the general framework is you say, I put down the toluene molecule. I put down a grid in space to describe the different regions of the toluene molecule. And then I build up the total wave function for a system by putting down little arrays on each of those grid points and connecting them all together. And that's the vision of what one really wants to achieve. In practice,
but how many particles at a time do you have to, what's the dimensionality of this problem, right? I mean, if you put 3 dimensions for every particle, what's the dimensionality of the whole thing that you have to model?
Yeah, so if the particles don't talk to each other, you can see even if each particle has 1,000 degrees of freedom associated with it, you don't multiply out that complexity when you have many particles. And that's what this technique is allowing you to do. Because in the arbitrary quantum wave function, if you represent one particle, one region with 100 bits of information, then you would need, for 1,000 regions, 100 to the 1,000, right? But you're writing down the total wave function in a special way that you actually only need a linear amount of information in the number of particles and the size of the system.
But that's only if you have just the two particle interactions, right? What if you have I saw that you took it up to 4 electron interactions for the benzene crystal.
Yes. So it's something which you can do so long as there isn't a very complicated many particle correlations involving all the electrons generated at the same time. But that's something that you do see in a system. So I mean, even if you're in a system where the electronic behavior of 7 or 8 electrons close together appears to be complicated, if you're over a large region in space, the behaviors tend to decouple. So it's always just there's some finite sort of cutoff on how complex it can become.
Thank you.
I'm not an expert in this, but I'm trying to keep up. And I was wondering, something you were saying in my head related to like Bezier curves or NURBS curves as far as trying to sum together what how they interact. Is that, am I getting a correct mental model there, or am I way off base?
Well, I might also, I'm not an expert in the things that you're saying, but as I understand, Bezier curve is a sort of a way of representing an arbitrarily complicated curve by breaking it down into little segments.
It seems very similar.
Yeah. So there's some similarity to that, but the thing that makes the quantum problem is kind of harder than the problem of approximating a curve. Mm-hmm. So the problem of approximating a curve, if you define the complexity as being related to the length of the curve, right, it should get harder and harder to approximate a longer curve. But nonetheless, if you approximate a curve that's sort of twice as long, it's really only twice as hard. You need to use twice as many interpolation points or little Bezier segments to make the curve to approximate the curve being twice as long. But in quantum mechanics, you're trying to approximate not just a curve that that has this one-dimensional line, but it's some function in a very, very high-dimensional space. Mm-hmm. And so you find that when you increase the number of particles from 1 to 2, the complexity doesn't double; it's quadratic, and if you go from 1 to 10, the complexity grows, explodes. Okay. So there's some similar themes of approximation, but there's some ways in which it's a harder problem.
Is there a distance at which you just disregard the connections?
Yeah. So is there like some distance beyond which you disregard, say, two particle, like different bits of the system talking to each other, for example?
Some ways of doing the curves we were just discussing is they might take n, where n might be 4 or 5 or something.
Yeah.
Even if there's 1,000 items, you only ever consider nearby neighbors as far as plotting the wave across them, because if it gets too far away, it's inconsequential.
So there is something like that going on. So that's, again, a locality principle, and that's also kind of what is saving you here. So it's kind of saying, like, if I'm trying to describe the curve of the wave function, so to speak, okay, with this funny function, then indeed you only tend to need to think about variables associated with behavior nearby, and that's a locality type.
I was wondering how big n might be in that, not, I guess, n is the whole set, but how far is it a handful? Is it 5 or 10?
Well, so maybe the right measure, because it's a little bit hard to compare the quantities you're saying with sort of the quantities that enter here, but maybe the right measure is like just how many bits of information, how many numbers do I need to keep track of at a time? Well, if you kept track of more and more, you'd be more and more accurate. So the way we do our simulations is we always keep track of the largest, as a scientific computing person, you just keep track of the largest amount of numbers you can keep on the biggest computer you have, right? And so that means billions and billions of numbers, because you typically can manipulate many gigabytes of data, even terabytes of data in memory these days.
Thank you.
I'm faculty at USC. I do machine learning and graphical model. I'm just visiting. So, great talk. I really enjoyed it. So I have a question about looking at how you decompose using the tensor multiplication. It reminds me graphical model. And one of the way of looking at a graphical model is it allows you to factorize a very complicated joint distribution into multiple, summation of tractable ones.
Yes.
But the problem with that is when you're starting to do marginalization, when you do conditional probability, it becomes a headache, right? So I'm just wondering, situation like this, how would you solve that? Second question is more about, you can easily imagine that special regions right now is pre-partitioned. But you can also think about maybe they evolve, or in some way you have to build a multi-scale sort of hierarchical organization of the spatial regions, so you have better trackability in terms of computation.
Right.
I'd just like to get some comments, and I don't know if you have time, maybe I can grab him after my meeting in the chat.
Sure. Also, you're not so far away at USC. You can come around to Pasadena and get some good food.
San Marino, so
you're in San Marino. Okay, yeah, you're just next door. So, so there's quite a few things in that comment. And so you brought up graphical models, and I have to say I'm no expert in machine learning, but I mean my understanding of graphical models is they're very close to statistical physics models. It's like you write down something that looks like a partition function. And the problem that you're referring to is something that I sort of omitted talking about. But it's when you go from the probability distribution itself down to a single number, that computation formally can look like it's NP-hard. So that's like saying if this actually is a representation of the normalization of the distribution, which is obtained by taking something at the bottom and contracting something at the top. So there are techniques that are made. If you just do this naively, the complexity of just creating a marginal distribution, a reduced distribution, is very, very high. I mean, it actually grows exponentially. But there are ways in which every time you contract tensors together, you reduce the information of them every time you add another contraction. And in that way, you can control the growth of the complexity. But what you're saying is one of the key questions about how to make efficient algorithms with these things. And perhaps we know from the physics side some things maybe that aren't used in machine learning. So that would be an interesting thing. The second thing you were mentioning was whether or not one should have some hierarchical distribution, decomposition in space. And the answer is, in principle, yes. That would only make the algorithms even more complicated. And no one's gone around to doing it. I mean, this is why like pieces of software like TensorFlow or other things that people are developing who are real computer scientists, is actually very useful because it makes it easier to implement these things. But in principle, yes.
I was curious, so you described how using tensor network methods you can conquer what is just a seeming complexity when in fact the numbers of degrees of freedom are much smaller.
Yes.
But in your second part, Google and I, when you were saying, hey, maybe we can use an emerging quantum processor to do chemistry calculations.
Yeah.
So this would, of course, be most helpful for cases where these methods break down.
Yeah, break down, right.
Could you give us some ideas for application areas where you would expect this to happen?
Yeah, so in some sense, this will be what I hope to talk to you guys about, and we can talk more. But the problems that, speaking in a non-rigorous way, okay, and the people here who prove real theorems, and I'm going to say something that's just very, very fuzzy, but the types of quantum states that are simple are states that are generated with the largest imprint from the Hamiltonians, the physical Hamiltonians. And so if I think about eigenstates of the Hamiltonian, the way if you take the lowest energy eigenstate or the highest energy eigenstate, the ground state or the highest energy state of the Hamiltonian, that's in some sense arrived at by applying the Hamiltonian to an arbitrary state many, many, many times, and it projects out that state. And so fortunately, it turns out that at the energy scales we look at, often we're interested in these low energy states, and those are very simple, right? But for classical computers, or relatively simple. But what a quantum computer can access is going to arbitrary states that are higher up in energy, and those become much more difficult to describe on a classical computer. So there are so for example, I take a problem that we didn't talk about, high temperature superconductivity. It's now possible for the models of superconductivity to do extremely good simulations of the ground state. But what happens at finite temperatures and what happens with the excitations of the system is much harder. I mean, I don't know if it's impossible for classical computers. I mean, I don't think so, but then I come from that side. But if they were easier on a quantum computer, that would be great.
So I think I probably agree with your premise that in general, the complexity of the quantum states that we see in nature probably don't grow exponentially in system size, in the sense that there is some locality to entanglement, and so once you get sort of past a certain correlation length, you don't need to keep track of all of the correlations.
Yeah.
But there's a question of, for systems that we might be interested in, just how much one does need to keep before getting to that point where the complexity stops growing exponentially.
Yes.
And it seems like there are a variety of systems, in particular ones that you might be interested in for catalysis, or in, say, material properties for like high temperature superconductivity, where you might worry that while formally you don't have unbounded exponential growth, you need such large you need to keep correlation in such large regions that it's just intractable in practice classically. Or you might worry that the structure of the entanglement is sufficiently complicated that you don't really know how to write down a good tensor network on SOTs, or maybe you don't know how to contract it efficiently.
Yes.
So what's your feeling about these things? Do you think that in general, for sort of all physical states, you will be able to find a good ONSOTs, and that the correlation length isn't so big that you can handle it classically?
So, I agree with all the things you're saying, and again, there's a couple points there to address. But what Ryan's saying is, even if I say that for most of the quantum states we're interested in, perhaps even all the quantum states we're interested in, you don't have this formal exponential complexity of quantum mechanics. And in practice, the complexity could be very high. Even if you have a polynomial dependence on system size and it was a high polynomial, that would be a problem. And that's very true. Whether or not that type of problem is the best problem to pit a quantum computer against a classical computer in an early test of quantum supremacy is an open question, because it comes down more to a game of prefactors. Because if something is exponentially scaling, you can always beat it, basically, right? I mean, it's so bad. But if you have two polynomials, and let's say the two polynomials are the same polynomial, you're down to a game of prefactors. And then I would say, given my perspective on science, I've always come from a classical computing world, the fact that we've done classical computing for so long gives us an inherent advantage for some time with prefactors that it would take some time to achieve with quantum computers. I mean, one day that prefactor might be gone. Now, there's just a practical question, though. Are there problems which today we can't solve on a classical computer, just right this moment? If I said you need to know the answer tomorrow, or in a month, or in 3 months, could we find? And there are systems like that. I mean, and those, of course, are systems which drive our research, right? But of course, I'm very optimistic that one can push the classical algorithms to study those systems. Otherwise, I wouldn't be sort of working on classical simulation. So I would say I think that we probably still can do those on a classical computer. But the honest answer is, right now, or for the next 3 months or 6 months, there isn't a computer to do it. And those are problems. Some problems of catalysis and superconductivity fall into that category.
In terms of scaling this up to larger problems and use in more areas as a general way of solving these kinds of problems, what do you see as the issue in terms of scalability? Is it the communication in the tensor network is so high that scaling this thing across many, many machines is a problem, or just the availability of, if I give you 1,000 GPUs to run this stuff on, would you be able to take advantage? Is it there's not enough capable grad students to be able to run all the experiments you want to do? What's the real bottleneck? Scaling problem?
Yeah, well, That's a really interesting question, which I thought, thought about a lot recently. And in a practical sense, when I started as a grad student, computers were really just getting faster, right? And now all that's happening is computers are getting cheaper, and that's a very different situation to be in. And if we're asking, can we push classical computing further to get another 2 or 3 orders of magnitude of speed up, it's not clear that you can do that with these general purpose chips. So I think that you can't parallelize these things more and more and more. There's just some limit, and we're maybe not yet at that limit, but we're close to that limit. And so that is a bottleneck. It's a bottleneck that classical computers are not getting faster, and these systems are not infinitely parallel. So I really think that what one should do is really build a custom chip to do this type of computation, and that's.
I mean, similar to what we've done with ML.
It's similar to what I understand you've done, but I know none of the details of because I don't think it's public.
Yeah, we're not talking about it yet.
With ML, right? And yeah, I was talking to a Googler about this, and I was saying, I really want to build this custom chip for tensor networks, and he was just saying they're silent the whole time. And then the next day, this announcement came out about these things. I said, oh, I asked him if he knew about it. He said, oh yeah, I knew about it, but I couldn't tell you anything. So, and it's actually really fantastic because the way these tensor network computations are set up, you're manipulating data. You think of these tensors as data that's held in different regions of space. They represent, and the computations only involve information from nearby regions of space. So if you set up a computer that way, it would never have to have this deep memory hierarchy where you have to go to a global memory, get some stuff and bring it back. Everything would just hold its local data and move it around next to each other. And building that in hardware would be fantastic. But it lies far outside my regime of expertise. But if you guys maybe already know how to do it.
Cool. Thank you.
All right, let's thank the speaker then.
Thank you.